Select the major product of the following reaction sequence. So we see that we are starting with a primary alcohol, and we're being told that we're using 2 equivalents of that. So that's not strictly necessary to come up with a product in this synthesis, but it is a good hint to let us know that we're bringing 2 of these molecules together. So we're taking this through a 2-step process. So the first thing we're going to do is we're going to treat this primary alcohol with PCC and dichloromethane. So PCC, pyridinium chlorochromate, and dichloromethane. So we should recognize this as the conditions to take a primary alcohol and selectively oxidize it to an aldehyde. So we're going to take that primary alcohol and we're going to make an aldehyde. And now technically we have 2 equivalents of this aldehyde. And so what we're treating it with in the second step is aqueous base. So we've got an oxidation taking place in the first step. And we'll say it's a selective oxidation. And in the second step, what's going to happen if you treat an aldehyde with a little bit of aqueous base is you can have an aldol reaction. And specifically, it's going to be an aldol addition reaction. So let's take a look at that aldol reaction to come up with the final product. So what's going to happen when you take your aldehyde and you treat it with a little bit of this aqueous base is you're going to form a small amount of the enolate. And so it's only a small amount because this is not a favorable acid-base equilibrium. So we're going to remove that alpha hydrogen to give the resonance stabilized enolate. So we're going to form a small amount of that. Most is still going to exist as the aldehyde form. And so you can draw the resonance stabilized form. I'm going to put the negative charge on that carbon atom so we can easily see that that is the carbon that is nucleophilic. And so since we've converted a small amount of this aldehyde into a nucleophile, the remainder of the aldehyde is still electrophilic at that carbonyl carbon, so we can have the nucleophile attack the electrophile. So it's going to react with another equivalent of the same aldehyde. And so we can see this nucleophilic enolate attacking the electrophilic carbonyl, and that's going to push these electrons up onto the oxygen. And so we can go ahead and draw the product of this. So we can see that we have still an aldehyde. Right? So we still have an aldehyde on this attacking enolate. The new bond will be between this alpha carbon and this carbonyl. So I'm going to draw this new bond. And so we want to make sure we have the rest of the chain from this attacking species. So we still need that isopropyl group. Okay. And so we have attacked this carbonyl. So that now has a negative charge in the oxygen since we've broken that pi bond. Then we still have attached to that carbonyl, there's a hydrogen that's understood to be there. So we don't need to include that unless you want to. But then we still have the CH2 and then the CH with those 2 methyl groups. So there's your CH2, CH, and the dimethyl at the end of that chain. And so with the water, then we can also add a proton to get this to the aldol product. Okay, and so we're going to pick out which product this is. So we're going to count carbon atoms. So we're going to count this main carbon chain. So you've got this 4 carbon atom chain with a methyl group on carbon 3. We're going to see the same thing here, 1, 2, 3, 4, this 4 carbon atom chain with a methyl group on carbon 3. And so hopefully we can recognize that once we protonate this, it's going to look the same as B. So again, let me number this carbon chain. So there's the 4 carbon atoms with the methyl group on carbon 3. And here's your other 4 carbon atom chain with the methyl group on carbon 3.